ask yourself when you're looking at a problem that is like that you're trying to factor? What's the first question?
Is there a GCF?
Perfect. And that's every single problem that we go over. Is there a GCF? Does number 9 have a GCF, Jaden?
It does. I pulled out 2x to the third.
Yeah. Is this a 3 back here? I might have wrote it wrong.
Yeah, it's a 3.
Yeah. There we go. Okay. So she said GCF, they're both divisible by 2, and then they both have x cubed. So when we pull that out, we are left with x to the 4th, still a minus sign, and then 16. So that's step 1. Every single question, is there a GCF? First question you ask yourself when factoring. After you do that first step, then you need to continue to look to see if you can do anything further with the problem. There are a couple of different factoring techniques that we now have discussed. And if I'm in the notes, so you don't have to switch back to your notes, but looking at the notes, the factoring forms that we learned in chapter 4 were as a general trinomial, which means it has to have 3 terms. Ours does not, it has 2. A perfect square trinomial, again, 3 terms. Ours does not, it has 2. The difference of 2 squares, so it's a difference and they're squares, they're perfect squares. Well, ours is definitely a difference. We can check to see if they're perfect squares. And then the common factor monomial, that's the GCF, we already did that. Yesterday, we learned the sum of 2 cubes and the difference of 2 cubes as well. So we need to look to see which one of those it fits, because right now we have 2 terms. So we have to determine, are these squares or are they cubes? And the first thing I would check would be, can I take the square root of these? So can you take the square root of x to the 4th? Well, what times what would make it x to the 4th? That's what a square root means. So can I take the square root of x to the 4th? Can I take the square root of 16? Or can I take the cube root of x to the 4th or the cube root of x or 16? Because those are the 2 patterns that we have that we can kind of use. So Ella, can you take the square root of x to the 4th?
Would it be x to the second?
Yeah. So x to the 4th can be written as x squared times x squared. Because when you're multiplying, you add exponents together. So x squared times x squared is x to the 4th. And then, oops, wrong parenthesis there. The square root of 16 we know is 4. So the pattern for the difference of 2 squares says I have to have x a minus b and a plus b. That's what the pattern says. So the pattern is a minus b, a plus b. And that's when I have an a squared minus a b squared, which means I can take the square root of them. So now I have it factored by taking the square roots because it was a difference of 2 squares. But then you have to keep checking. So you need to keep asking yourself, is this completely factored? So if I look at my new step, inside those 2 parentheses, there still says an x squared. And anytime it has an x squared, that's when you need to check it. Can it be factored any further, or is it prime? Is it completely factored? Well, if I'm looking at this pattern, a squared minus b squared, I see I have that pattern again right here. A squared minus b squared. That is the difference of 2 squares. So that means this can be broken up again and be factored even more. So I can factor this as x minus 2 and x plus 2. However, the one next to it says x squared plus 4. if I look at my pattern, the pattern says a squared minus b squared. So that x squared plus 4 is a sum of two squares, and it does not factor because it doesn't match the pattern. So this x squared plus 4 is called prime. It cannot be broken down any further. So it must be a difference of two squares. It cannot be a sum of two squares. So make sure you're looking for that. There is no way to factor this. It is not factorable because it is prime. So I cannot factor it as x minus 2 times x plus 2 because that gives me x squared minus 4, which is not the same. So this should be your factored answer for number 9. Now notice it was really 3 steps of factoring. The first step was the GCF, and then we used the difference of two squares. Any questions with number 9? So after number 9, 10 through 17 used perfect cubes. And I'd like you to go back into your notes, and we're going to talk about a couple more problems factoring wise. So if you can go back into your notes and look at page 12. Numbers 10 through 17 were all perfect cubes from the homework. So they all fit a specific pattern. Your homework tonight is going to be broken up in the same format. So it's going to be grouped into the certain types of factoring so that at least it's not all mixed together. Tomorrow the factoring will be mixed together, but today it's kind of grouped. These are perfect cubes. You have to use factor by grouping for these. This group you're going to have to solve. Yesterday, we talked about the pattern, lots of factoring patterns, the pattern of the sum of two cubes and the difference of two cubes. So this one is allowed to have a sum and it's allowed to have a difference, but they must be cubes. So if I look at number 1, down at the very bottom of page 12, in the independent practice, we have 8x cubed plus 64. Well, that x cubed is an indication that you're going to use the sum of two cubes since it says x cubed. But the first question we need to ask yourself would be, is there a GCF? So Brooke, if you look at number 1 with the independent practice, is there a GCF with 8x cubed plus 64?
Yeah, you have to pull out 8.
Yeah, when you pull out an 8, Brooke, what do you get?
X cubed plus 2. No, I'm sorry, it's 8.
There you go, perfect.
No.
All right, so now we have x cubed plus 8. Well, I know that I can take the cube root of x cubed, but I also can take the cube root of 8. So those are perfect cubes. We want to factor this using the perfect cube pattern. So the perfect cube of x cubed is just x. The perfect cube of 8, or the cube root of 8, is 2. So that would be my a and b term. And then this factors as a pattern. So the pattern says a, same sign, which is a plus, and then b. And then it says a squared, opposite sign. So I started with a plus, it has to be a minus. A times b, so multiplying them together, always positive, and then b squared. You must factor this with the pattern for the sum of two cubes. I saw a lot of students factor this as x plus 2 quantity cubed, and that is not how it factors. So that does not work. It does not factor like that. X plus 2 cubed means I have x plus 2 times x plus 2 times x plus 2. And if I multiplied that together, I would get a very big polynomial because that's what we did before break, not a little polynomial of x cubed plus 8. So this is not correct. Does anybody have questions? So a lot of you need to go back and look at 10 through 17, especially if I left you comments. Make sure you're factoring them with the perfect cube pattern. All right, so we're going to continue to do more factoring, as I said, just lots of factoring practice today. So I'm going to the bottom of page 13. And it just says conclusion independent practice, but we're just going to work through these to kind of get some problems done, and then we're going to continue doing some more factoring. So let's look at this problem here. This is a 4-term polynomial. We have 4 parts to it. Grace, what do you think you would do first with a problem like number 1?
Isn't this the kind where we like split it into the 2 different sides?
Yep.
Okay, so you would take the first 2 and you'd pull out a GCF of x squared, and then that would be you'd be left with x plus 2.
Okay, perfect. The next pair?
And then the second one is you can pull out negative 25, and you'd be left with x plus 2.
Nice. That's called factor by grouping. So you're putting 2 of them together, pairing a group of terms together and pulling out what they have in common. The next part of grouping is to continue to make it into a factored problem, which means I take the pair in front and group them together because they are like terms. They're both being multiplied by that x minus 2. So that's why you're allowed to group them together. And then we have the x plus 2. That becomes a group together. Individually, they are being multiplied by x plus 2. So together, they can be multiplied by x plus 2. So now, before you move on to the next problem, we have to ask ourselves, is this completely factored? And to check that, look to see if there's something that says x squared. If there is, then does it match a pattern that we can continue to break it down? Riley, can x squared minus 25 be factored anymore?
Yes.
And how does it factor, Riley?
Would you do the pattern where it's like a squared minus b?
Yep.
Mm.
So this is the difference of 2 squares. If you take the square root of both of those, what do you get?
X minus 5.
And
X plus 5.
there you go. And then you just bring down the x plus 2. We already got that from factoring, so it doesn't change. It is just an x. And when it's just an x, that's when it's prime. It's factored completely. So my final answer, x minus 5, x plus 5, x plus 2. Questions? All right, let's look at number 2. This one looks a little different. X to the 4th minus 14x squared plus 45. This is a trinomial. It is in the form ax squared, but really it's x to the 4th, bx squared, and then plus c. So there's 2 different forms of trinomials that we could work with. This is the same type of factoring that we would use if it said ax squared plus bx plus c. It's in the same pattern, except the first term is x to the 4th instead of x squared. So we're going to try and factor it by taking a times c because it's a trinomial. So anytime it's a trinomial, we can try and factor it using a times c. So Malachi, a times c is 45. Can you give me two numbers that multiply together to be 45?
9 and 5.
Yeah, and what are both of them going to have to be if it's negative 14?
Negative.
Yeah, negative, of course. So we're going to try and factor this. We keep the x to the fourth. Malachi just told me negative 9 and negative 5. So I'm going to write negative 9x squared because it said 14x squared. Negative 5x squared, and then plus 45. So you're factoring this using that AC grouping, but we have x to the fourth and we have x squared. So now it's a problem like we have above, where Grace said, let's pull or group values together and pull out what they have in common. So Jordan, what could I pull out of that first pair, x to the fourth minus 9x squared?
X squared.
And what do you have left when you pull out an x squared?
X squared minus 9.
Good. And what would you pull out of the second pair?
Negative 5.
Yeah. And then we still have x squared minus 9. So you group the x squared and the minus 5. And then we group the x squared and the minus 9. So here's the part where, before moving to the next question, look at your answer and ask yourself, is it completely factored? Or does it match a pattern? Well, these are both binomials. There's two of them, and it's a difference. So we have a difference. Is there anything you can do with one of these factors or both of these factors to break it down further? Annabelle, what do you think? What could we do to continue to factor this?
You can factor x squared minus 9
And why can we factor this one?
because it's the negative one. I forget what
And 9 is a
perfect square.
perfect square. Is 5 a perfect square, Annabelle?
No.
No. So we can't break that one down because it's not a perfect square, but 9 is a perfect square. Annabelle, how would that x squared minus 9 factor then?
X plus 3, x minus 3.
Excellent. Nice job. So I cannot take the square root of 5, but we can take the square root of 9. So that one does get broken down. So now it's completely factored. Again, this first one cannot break down because we cannot take the square root of 5. It's not a perfect square. But we could break down the second into x plus 3, x minus 3. All right, the last one on this page. If you haven't started this, I'm going to just kind of work through it. See if you can work through it as well. This one has 4 terms, so I notice that there's 4 terms. I can pair or group things together. Taking out what they have in common, that would be an x squared, leaving me with an x and a minus 1. Don't forget that minus 1. When you take x squared from negative x squared, you get a negative 1 there. The second group, I could take out a minus 4, and I still get an x minus 1. I can group then the x squared and the minus 4 together, and then we have x minus 1. So Ava M., are we done factoring this? Is it completely factored?
No, because you have to split the first one up.
Awesome. And how does it split up?
It splits up into x minus 2 and x plus 2.
Perfect. Nice job. All right. Any questions? So we're going to just do a couple more factoring problems. Lots of factoring. If you go to the next page, it's really not the next page. It's, I guess, page 15. Same questions, factor. Factor completely. So same type of questions, we're factoring completely, breaking the problem down. I will tell you that part B here is a little more interesting than part A, but they're both pretty good problems. So we have 16x to the fourth minus 256. Julia, what's the first question we ask ourselves when you're looking at a factoring problem?
If there's a GCF.
Yeah, is there a GCF here? Can we take 256 and 16? Are they divisible by anything?
I'm checking 1 second.
Yep, that's fine.
So you can take 16 out of 256.
Yeah,
and
what does that become?
it becomes minus 16.
Yeah, nice. So first question, is there a GCF? Yes, there is. Now the second question, does it match a pattern once you take out that GCF? It's not a trinomial. So it's not a trinomial, it's gonna have to match a pattern. And that's where you just wanna check, is it a square root pattern or is it a cube pattern? And since it's 16, I know I can take the square root of 16 and I can take the square root of x to the fourth. So x squared minus 4, x squared plus 4. So x to the fourth is x squared times x squared. And now, considering all the other problems that we looked at, whenever you have an x squared and a minus, then I can continue to factor it. So we have the 16 as the GCF. I can take the square root and get x minus 2 and x plus 2. However, the next one behind it is plus. It is not a pattern when it's x squared plus 4. It's a difference of two squares. It doesn't work if it's a sum. So that x squared plus 4 does not factor any further. Again, it must be a difference in order for it to be factorable when you're dealing with squares. So a difference of two squares. See if you can factor part B. So GCF first, is there something in common? Madison, is there a GCF for part B?
Yeah, I pulled out 3.
And what else besides a 3, Madison? What else do they all have?
I also pulled out y to the third.
And then what were you left with when you pulled that out?
So I didn't like fully do it yet, but I have y to the fourth minus 5y to the second plus 6.
Yep, that's perfect. All right, so let's look at this. Madison, how many terms are here right now inside the parentheses?
3.
3. So when it's a trinomial, that's when we're going to then factor it with that regular factoring AC grouping method. So we need two numbers that multiply to be 6. Madison, two numbers that multiply to be 6, but combined to be -5.
Would it be -6 and -1?
If we did that, that would make -7 when we added them together. What else makes 6?
Would it be? We did this yesterday, didn't we?
I think Jaden did it, I think, right?
Yeah,
I
that
think
was
she
that
gave
was
us
me.
the same numbers as well.
I did.
Okay, it's early in the morning.
2 and 3.
There we go, 2 and 3. So we're gonna try and factor this with that grouping. I'm gonna just kind of forget about that 3y cubed for a minute, just so it doesn't get inside and messy. So I have y to the fourth minus 2y squared. So that's the difference. It has to be y squared now because it's 5y squared minus 3y squared, and then plus 6. So factor by grouping, I can pull out a y squared. Factor by grouping, I can pull out a negative 3. And then I get y squared minus 3 and y squared minus 2. And then I squiggled my GCF so that I wouldn't forget to pull it back down. Madison said take out a GCF of 3y cubed. So the last question before you move on, are these completely factored? That means, can I take the square root of them and break them down further? Well, 3 is not a perfect square. 2 is not a perfect square. So if they're not perfect squares, if you can't take the square root of them, then you have completely factored the problem. But make sure you're checking that. So can you take the square root of that number? If you say yes, then it can be broken down again. If you say no, then we don't have to factor it any further. Any questions? So the remaining 2 problems on here deal with solving, which is essentially the same thing, except we're going to solve for x. And then there's a word problem on here. So if you look at number 4, it says, what are the real numbers solutions? So anytime it says a solution, we're still going to factor it, but then we're going to solve each of those factors for x. So you're still using the same process, but you're solving each factor. So if we look at this example, x to the 4th plus 9 equals 10x squared. Gabby Snyder, what do you think you would have to do first in order to try and solve this?
Wouldn't you have to bring the 10x squared over to the other side?
Exactly. So we need to get everything together on one side. When you're writing them on one side, make sure you write them in order. So x to the 4th, 10x squared goes next, and then plus 9. So we want it to look like that trinomial pattern so that it's in order. The powers should decrease. So now, just like the one we did above, it's a trinomial, and we have a 9. We know it could be 3 and 3, but that doesn't give us negative 10. So it's going to have to be a negative 1 and a negative 10, or how about a negative 9, to make negative 10. So x to the 4th minus 1x squared minus 9x squared plus 9 equals 0. So this is factor by AC grouping. Group the pair together in front. Taking out an x squared still leaves us with an x squared and a minus 1. The second pair, taking out a negative 9, leaves us with an x squared and a minus 1. So again, before you do anything else, is it completely factored? Lacey, can we factor this any further? Are those parentheses able to be factored further?
Yeah.
How could you break those down?
You could break down the x squared minus 9.
Okay, because we can take the square root. So what does that get us?
X plus 3 and x minus 3.
How about the next one? Can we take the square root of 1?
Yes.
Yeah, so how would that break down?
X plus 1 and x minus 1.
Yeah, nice job. This one factored a lot. we broke it down all the way because both of those final factors, they're both a minus sign and they're both perfect squares. Now, this is factored completely, but it says find the solutions. How do you find the solutions once it's factored? Valerio, how would I find the solutions once it's factored?
You would use the zero product property to set
Excellent.
each one equal to 0.
Excellent. So it is the zero product property. Great job for remembering the name of that as well. Each one of these individual parentheses is set equal to 0. If you want, you can skip this step right here. You don't have to show them each individually equal to 0. Together, they're equal to 0. The zero product property says individually they're equal to 0 as well. So if you want to skip that step, you can. But in your mind, you're mentally setting each one of them equal to 0. So I have x equals -3 from the first one, +3 from the second, -1 from the third, +1 from the fourth. Those would be our 4 solutions. So, Jaden, what was the power of this polynomial? Or what is the power of the polynomial?
Do you mean like the whole thing or like the original problem?
So what's the largest power exponent that you see in the problem?
Oh, the fourth power to the fourth power?
Yeah, to the 4th power. How many answers do we have?
4.
Do you think it's coincidental that they are the same?
Probably not. No.
Probably not. Yeah. So when you're looking, the biggest power in a problem gives you an indication of how many solutions there should be. So the power of 4 means there's really 4 x's. In the last chapter, we always had x squared. And when we solved, we ended up getting 2 values for x. So the power should match the number of answers. So we're going to stop with this last problem here. We'll do one more factoring problem. And then I guess we'll save the word problem for tomorrow. So see if you can find the real number solutions. That just means we want to find the answers. We want to solve for x. To do that, we need to factor. And when you're writing these out, write them in order. Don't forget to check for that GCF first. So I'm just working through the problem using everything that we've just talked about. So I took out a GCF. I then used the AC grouping method. And I'm now down at the bottom. And my last step is to check to see if I can factor anything else. And I noticed that the first one, I can take the square root of 4. So I can factor that. I have a 2x. I can take the square root of 4 and make it x minus 2 and x plus 2. I can't take the square root of 3, so I'm going to just have to leave that as x squared minus 3. So Valerio said it's the zero product property. You're going to take each one of those x's and set them equal to 0. There is an x that we pulled out with a GCF. That gets set equal to 0. Then there's the x minus 2. There's an x plus 2. And then there's still the x squared minus 3. Each one of those factors gets set equal to 0. Zero product property. Every factor must be set equal to 0. If it contains an x, it's a factor. And it's going to give you a solution. So my first answer, if I divide by 2, I get 0. The second one, I have a 2. And the third one, I have a negative 2. However, the last one that I have written here says x squared. So if I solve for this, I have to take the 3 to the other side and I get x squared equals 3. Ella, how would you solve for something that says x squared? So we have x
You
squared.
would do the square root of 3.
Yeah, we need to take the square root. So this is again back from chapter 4. Ella, when you take a square root, do you remember what goes in front of every number when we take a square root to solve?
An I.
Not an I, because it's not a negative square root. That would be if I had the square root of negative 3.
Plus or minus.
There you go, plus or minus. So that would be from last chapter. When you're solving for the problem that has a square root in it, anytime I take a square root to solve, we need a plus or minus in front of that answer. Now, just going back with the last problem, the power is 5. You should have 5 answers. I have 1, 2, 3, and then a plus or minus gives me 2 more answers to make 5. Does anybody have questions? So your homework is a worksheet. It was posted to Google Classroom. I apologize that it's a little blurry, but I think your eyes are young enough that you can handle it. My better copy, I don't have a digital copy of this, unfortunately, and the better one that I have is at school. So it's a little blurry. I apologize, but I just didn't have a better copy at home with me. I'd like you to do the odds of it. Do not do the word problem because we didn't get to the word problem. So do the odd problems of the worksheet and skip the word problem. We'll talk about that tomorrow. Have a fantastic day. We'll wrap up factoring tomorrow and look at a little word problem. Have a good one.
Have a nice day.
Thanks, you too. See you later.